Good afternoon. This is just a piece of kit that I picked up from an auction site. This is an 8508A Vector Voltmeter. And you probably would have seen, or you might have seen the previous video I did on the 8405A, I think it is, which is the previous version of this. It's an analog Vector Voltmeter. This is a digital one. So what I wanted to do was just take you through some of the features of this unit, talk a little bit about how it works, and with me today I have a friend of mine who was in the Navy for a while, worked on a great grey war canoe, and did test and measurement stuff, and now he runs a test and measurement lab at one of the companies here in Seattle. And so I thought at the end of the video we'd take a look through a couple of the photos that he took of it and talk about how the lab works and day-to-day stuff. So with that, just introduce Miguel here. Miguel, say hi to everyone.
Hey everybody.
Yeah. So the 8508A is really sort of, you can consider this as a proto network analyzer. What it does is it enables you to check the phase and magnitude differences between two test ports, and in this case this is test port A here and this is test port B, and I can put a signal in here. The unit will effectively lock to that signal, measure it, and then calculate, depending upon what I've selected, the difference in input B. Now, you were saying that you used something similar to this when you're on the ship?
Yeah, we used to use them for, I'm trying to remember, it's been such a long time, and I think it was for power sensors. And it was a pretty sweet setup there. When I was there, when I was in the Navy, we used a lot of older equipment. One of the oldest ones was oscopes with using the viewfinders.
Right, the little shroud.
Yeah, the shroud. So that's my experience with some of the other equipment. When you said on this one right here, your the other one was analog. Were you saying the display? Was it a meter?
Yeah. They had the previous one had probes. So this particular unit, you can take out these modules here, and you can get a probe set, and I think there's one other, I forget what it is. But the probes basically enable you to go into a circuit and sort of measure on component levels around the trace or so on.
Yeah.
This unit here with the N types on it increases the bandwidth. The previous one, I think, was 100 kilohertz to 1 gigahertz, and I think this one here with this unit is 300 kilohertz to 2 gigahertz. So you've got slightly bigger range on it, up to about 15-16 dBm.
Was that the meter, the analog meter? Was it 1 meter where you found an all and then showed the degrees?
No, it was 2 meters side by side, and you could get it to read the magnitude, or you could tell it you wanted the phase between them, and so that would let you go do that, but it didn't do any calculations. So what this unit can do is go in and make calculations on the values that it's got, and then provide that information to you so that you don't have to go do it yourself.
I just find these amazing. They're kind of like a Smith chart in real life, where it shows you deflections and gains. If you understand what you're looking at, which I don't, because I'm more of an RF mechanic, you can do some impressive stuff with these things.
Yeah, and in fact, this has a feature over here called normalization. And so when you set it into its impedance mode, you can actually tell it to go to give you the real impedance. It's not the actual impedance number. So you get the complex impedance, real and imaginary components. But you can also then push it in the system impedance setting to go normalize, and what it will do then is it will actually normalize those values for you.
Okay.
So you can then immediately just tag them straight on your Smith chart. You don't have to do any of the math to go and create the Smith chart. And then you would just simply vary the input impedance, the input frequency to move around the Smith's chart and record your values.
Now, like a vector voltmeter, you're using these because, as you were saying, it's the inboard testing. You're looking at the reaction of like inductance and impedance and capacitance in a board within a series of circuits, RC, LCR, whatnot.
Right. You're looking effectively with these. It's much more the traditional device under test. You've got your device. You plug a cable into one end, a cable into the other. You can read it. Whereas with the probe stuff, the device under test can actually be parts of a circuit. So you could imagine going in and having an amplifier that you've built and on multiple stages. And so what you could do is you could go in and say, I'm going to look at the input to the first stage of the amplifier and see what that's doing in terms of phase and magnitude. And then I could do
for your theory.
Then you could go down the process looking at the whole bits and pieces, right?
Well, they also remind me of, in the Navy, we dealt with Huntrons. Are you familiar with those?
No, I've never.
So the Huntron would be a device that, a classic troubleshooting device where there's two types. One would be component, so it would show like the L shape or rise time, whether it's capacitance or inductance. Right. The other one, you would plug a board into it, and it would shoot the signal all the way through the board and through the lines, and you would have a gold disc, which was the ideal reactance of signals and whatnot. Put that in there, and then it would compare to what you're actually seeing, and then that was your form of troubleshooting like a board.
Oh, nice.
Yeah, it was pretty neat.
Yeah, they have. I've never used them, but I've seen manufacturing facilities that have automated testing stuff that do similar sort of thing. That you can drop in an entire board, and then in a custom sort of bed of nails type approach, it'll put stuff down on the board, and it'll run the board and measure that. Did you ever use the signal analyzers? Not signal. Hewlett-Packard did a signature analysis, right, where they had for their first digital stuff, because it was a brand, moving to the digital world was a big change. And if you read a lot of manuals from the era before this, a lot of the theory of operation and that included a bunch of information for the people reading the theory of operation about the difference between the traditional analog world and the new digital world, and like how AND gates and OR gates and things worked and so on. Yeah. Because it was a real change in the technology for the technicians and the service people that were working on the devices. And so they came up with a thing called a signature analyzer, and basically you could connect it to a board and run or set the board into a test thing. Yeah. And then it would give you a 4-figure hex number. Okay. That would basically analyze the signals and say, I'm getting this. And then you could check against the manual, and the manual said, say, you should get 5045 here.
Yeah, no, I never dealt with that.
Never dealt with this?
No. But it kind of sounds like with the Huntron. I was saying, the Huntron 2000 Plus, it sounded very futuristic. That's why it always stood out in my mind. And then when I realized the purpose of it, it was very focused on us, component level troubleshooting, especially on a ship when you're out to sea, and you try and do your best. But in the end, when you come to the civilian world, everything's modular. So,
these would tended to be more as an engineering instrument, at least what I've seen them being used in, where they're used at the desk of an engineer or somebody actually designing a circuit, rather than a piece of equipment for test and measurement in the field.
Well, and that's why I asked what I was asking, because as you mentioned, my experience is test and measure. And that's why I've embraced the test and measure, because the great thing about it is I'm not making anything new. Everything's predetermined outcome for the most part, except for like software, which everybody can relate to. Test and measure is my thing. And the reason why I was asking these questions is because in where I'm working at, I see a lot of ENAs, a lot of PNAs. Yeah. They're all coming through, and these guys are using them for checking out board signals, and they actually just component signals, because they want to verify, like, if we buy 1,000 of these capacitors, whatever, what are we getting, repeatability and all that stuff.
Right. Well, a lot of that is the case of, doing your supplier checks and things. Yeah. Your supplier will give you a data sheet that says a component has to be, here's the the bell curve or whatever on a component, and here are the tolerances, and you want to go and get a set of components randomly that they give you.
Yeah.
You test them. You say, yep, they're within the curve.
Exactly.
Okay, we're going to trust that our supplier is shipping these things correctly, and generally you do that on a regular basis just to keep everyone.
It's good Q&A practices for sure.
Yeah. Plus, you've got to make sure that the engineering intern has a job because
and the Cal Lab, make sure your Cal Lab has a job because they got to check that stuff. So it's very important.
And you can actually see. So this is actually on this module here below here. We can see antenna and exciter. Or at least that's what I'm thinking. EXCTR is.
Has to be.
I'm not really sure how they would have set that up. But in this particular case, this really does look like it's actually used in a test sort of environment. That sort of thing strikes me as being something that would come from, like if you had a transmission studio or something where you would have this set up.
Okay, monitoring
all the time, and you would go and look at things. So
you think it's more used in a active production setting instead of like a manufacturer?
I don't think this was used in a manufacture case, but it could have been. We were talking about this a little bit before we started recording. I just don't know because typically when you measure off port B, you're measuring the ratio or the differences from port A. And the exciter is usually a smaller amplifier that you would then feed into the output amplifier for your transmitter.
Yeah.
So I'm not sure how they would have had this set up with the antenna and the exciter.
Well, also theoretically, couldn't you say you had a standard antenna, somebody knew what to expect the response was. Right. Maybe you were checking exciters and seeing what the antenna was seeing. Would that be a thing?
You could be. Yeah.
I'm just
Yeah, you could be saying you're tapping the signal out of the transmitter from the post exciter, but before you go into the final amplifier stage, and then you're taking the signal that comes out of the final amplifier, capturing it via antenna, and maybe comparing it that way. That's certainly possible.
Right.
But that's what it leads me to think that this wasn't used in a design case, or it wasn't used in a calibration case. So I think,
for sure.
Definitely I think this was used in some form of production test.
Yeah. Well, even in the monitoring in a studio or something, right?
Yeah. Yeah. All right. Well, let's go take a quick look through the front panel here. We have the module. We've talked a lot about that. These units come with a test out. This is basically a verifying that it works, not verifying that it's in calibration.
Sure.
So it puts out a rough signal that you could feed into here and here, and then check that it's actually
expected outcome.
That you're getting what you're getting. These displays are digital displays, and you can see unlocked here. And the reason you're seeing unlocked is how these units work is they take the signal in on port A, and then they lock to that signal. So that's how they get their what the frequency is and so on. And then that enables them then to pick up the signal on the second port, match and work out what the results are there. So at the moment it's saying unlocked because we don't have anything being fed into port A.
Do you know what the internal reference signals are? I know 10 meg is generic for everybody, but
this doesn't display frequency, so what you're getting, I don't think it has it doesn't have a 10 meg in because it doesn't really care what the frequency is.
Well, no, I've seen some units that have internal, no outputs, but
an internal thing
for references, always a 1K, I believe, and a 10K or 10 meg.
I don't know. I'd have to have a look at the schematic.
Okay.
I don't think it really matters. I think they derive. Well, clearly they'd have an oscillators of some format because they've got to drive the digital stuff in there and so on.
And know something, right? So know that this is a 10 meg signal.
Right, and this unit here, the module would have oscillators in there because it's going to need it's going to have some local oscillator stuff to be able to pull the signal in and drop it down and get an IF and so on. But because it's not dependent specifically on the frequency, you wouldn't expect to have, a 10 meg input, or at least I wouldn't expect it to have a 10 meg input, or have a high stability crystal oscillator or so on, because it's fundamentally locking to whatever the frequency is here, and you don't really care whether that is 1.01 gigahertz or 1.02 gigahertz.
Sure.
What you care about is the magnitude and phase differentials between the 2 points, right?
See. Okay.
So, All right, so where were we? So this lets you test whether it's on. The unlocked, we talked about how it locks that first signal. You can set some of the ranges. You can change the magnitude displays. And this is all the display control area here. This here is where you can set your measurements, and you can say, set your displays. I want to have display 2 on or display off. I want to change the phase, the magnitude, that sort of thing. And we'll see some of that when we put a signal in. These are the functions over here. One of the cool things that this unit does is it enables you to do reflection measurement.
Yeah, that's pretty good.
And get information about things like the SWR. And in fact, we'll take a simple SWR measurement just to show how you might use the unit in real life.
Cool.
And to do that, what we're going to do is we're going to use a 778D directional coupler. And that's the lower frequency directional coupler. They have a 772, which goes from 2 gig to 18. But this is from 0 to 2, and actually we're going to, it's not 0, it's like 0.1, so it's like 100 megahertz to 2 gig. We're going to take like a 100 megahertz signal and feed it in. Now, a directional coupler, I did a video pulling one of these apart, showing the internal construction of them.
Oh, right on.
It's basically a strip line module. Fundamentally, how it goes is we input our signal in here, and this signal comes in and comes down a major strip line and pops out to the device under test there. And let me get that more in shot so you can see it. What it also enables you to do is to couple an incident and reflected signal, and that lets us tell what's coming back from the device under test and how much power we're putting in. And you'll lose about 20 dB on each of those ports.
Is there an attenuator in here doing that? Or?
No, it's because of the way the strip line works, because
Okay.
you have the main transition line, you have the sort of the main transition line, and then you have a coupled transition line over to here.
Yeah.
And these are a very accurate 50 ohm terminated loads.
So it's essentially just physics of why it does.
Basically, yeah, it's the field
Gotcha.
between the two transmission lines. The whole thing on transmission line theory.
It's amazing. Well, everything, I think, it comes to RF and any electronics, you can specialize in one thing and be busy for days.
Yeah.
You know?
Yeah.
Yeah.
Well, transmission line theory and all that is very math oriented.
Yes.
It's a bit of a dark art. You've got to know your calculus and things like that.
Yeah.
Well,
antennas,
antenna, same sort of thing.
all that stuff. So much.
That's why drink of the day is, in my case, it's a hard seltzer.
Red Hook.
Miguel's having a Red Hook IPA. But I make sure with with that sort of stuff, you needed the drink of the day to get through the classes on it.
I appreciate that. That's how I got through the Navy. My RF microwave class was in Biloxi, Mississippi. I was in both calibration there and in the advanced microwave class. So that's my experience.
Yeah, I did, while I was at university, I did 2 6-month courses. They're not 6 months because, 2 semesters.
Oh, sure.
2 semesters a year. I did Systems of Control A, Systems of Control B.
Oh, my God.
In neither of those labs did I ever actually build any control systems. It was all just the math on how to control stuff.
Which is essential, fundamentals for everything. Even like when, and this is why I have appreciation of what you do. For going through the old stuff, have you read that calibration book that I gave you?
Yeah, that's fantastic.
How it talks about the terminology. Millimeter wave, it applies to everything, whether it be dimensional or RF. It's such a great understanding for the fundamentals.
Yeah. So moving on, we're actually going to use the 11570A, which is this kit here. We're going to use parts of this. This is the accessory kit for the previous
That looks sexy here.
version. Yeah. And I talked about the probes that came on here, and you would imagine that these probes have tips. They're cabled in, and the probe has a tip.
Yeah.
And so you would take the probe, stick it in there, and then these things are a T that can go into a transmission line, and you can just drop the probe straight in there to pick up your signal. In this case, they're tapped directly on N types, but with the other ones with probes, they help you get those signals. Yeah. Power divider, some isolators. The isolator tips are most used in circuit work where you You want to make sure that you don't load down a circuit or change its operation based on the impedance of your probe or so on.
That's something I never thought about, circuit testing. As far as I heard a conversation in a certain place where I work at, and I was one of the things in consideration. One of our mutual people that we know, Gary, he pointed it out because the engineer was asking him, "Hey, your probes, I need something that does this." And Gary's like, "Well, did you consider the impedance and blah blah and reference the rise time, all that stuff?" He's like, "Shit, no."
Yeah,
like that's something you definitely have to consider when you're troubleshooting and doing everything else you're doing.
Right, and a lot of the higher frequency RF or an oscillator work or so on, you want an active probe because that will help you, minimize the load or what the appearance on the circuit, so that you'll always have some appearance on the circuit.
Yeah,
but you want to make it as small as possible so that you can have as least impact as you can. And then in that reflection measurement, we're going to use the little short they have here.
Nice. And
we're just going to use that as a reference standard. This instrument, you can actually also just use a T and one of the 50 ohm. These are I think these are 909, there's 908As, so these are DC to 2 gig.
Nice load.
And you can just use those as a reference, and then you can actually do reflection measurements just straight off a T.
Nice.
Up to about 100 megahertz, they say.
So this is still a pretty good, useful tool when it comes to home electronic stuff.
If you were doing, if you were a ham and doing some RF stuff and building your own amplifiers and things like that, one of these can be a very good tool. If you're going to create your own, anything where you create a Smith chart, one of these can be a very good tool for you. The reality is that network analyzers, vector network analyzers, that have gotten so cheap these days, comparatively. Let's be clear, that even a smaller, even a hobbyist and so on can get a low end vector network analyzer. In fact, I have never used them, but I've read good things about these nano VNAs, they refer to them, which basically, I think they were originally Arduino based, but now they're, I think they're FPGA or something, and they go up to, 50 megahertz or so on.
I know of a company, Copper Town, I think it is, and all their stuff is modular as well.
They're still but they're still a professional thing, and so that's
still high end.
Yeah, you'll pay quality for that, but it's these nano VNA things you're buying off eBay or Alibaba or so on, right? Full of coronavirus.
Just Jason.
Let's move on. And so, you can also do direct power measurements, and then, as I said, normalization and so on. And these are GPIB enabled.
This power measurement, would you consider this more like a poor man's power meter?
Yes, you would. You very much not. You're not using this as a power sensor. Like an 8400 series or something like that to get really accurate
attenuation, all that.
Values of power. My 8902A can read down to I think 1,000th of a dBm. A lot of the modern the replacements for the not the 437s, the next version on the
432s.
No, the
forward.
For
438.
No, I can't remember the name. It's like the more modern ones that have digital readouts and so on.
E4419.
Yeah, the E4419s and the EPMs and so on. They have, using those sensors. Then they have the USB-based sensors and that, which are even more, that have better accuracy and so on. And then they have the N432, which is the modern thermostat thing, which is highly accurate. But in the sense of I want to get an idea of what my device is outputting. Is going to be good. It's going to be more than good enough for the average hobbyist. I can't imagine that you'd ever need anything more than this if you weren't looking to do serious measurement. Now, some of the hobbyist guys do serious stuff, right?
But still, considering this is, all the old HP gear, the reason why I have so much respect for it is because it's all still solid state. I mean, when you drop something from 1960, 5 feet on the floor, and it still survives, but you drop something from 2010 and you drop it on the floor and it says, nope, I need to be rechecked. We got issues.
Yeah, well, the difference is the 2010 stuff you can actually pick up with one hand, whereas the earlier stuff, like this 8340B that we're using, it's 2-man lift.
Well, I still have an 8663 Alpha that I don't pick up until I really need it because it's a really good oscillator reference. But other than that, I don't want to.
Yeah. All right. Well, let's hook up. Let's hook up the directional coupler to the meter, and then we'll do a test of some SWR. Okay. All right. So now we're cabled in, and we're about to be able to go. We're going to use the directional coupler here, and what I have is these two 908A loads. I have a little T and the short, and the short we're going to use as the reference point for setting up the reflection measurement. Now, what are we going to measure, and why do I have the two loads? Well, what I have here is, let's see if we can get that in just a little math here. Basically, what I'm going to go do is I'm going to take these two loads and then screw them together. Thank you. So that now what we have are the two loads effectively in parallel, which drops their impedance to 25 ohm.
Okay. Oh yeah.
So
big difference.
Yeah, you can actually get known VSWR stubs that'll, like terminations, that'll have a known characterized things like this is a 2.2 to 0 or like a 2 to 1 or 3 to 1 or whatever sort of thing.
Well, this is a good at-home standard though.
Yeah, because these things are pretty accurate. So it'll come out somewhere around 2-ish.
But once you know your reference, you're good to go from there on.
Right, right. And if I really wanted to get an accurate SWR, I would use the. I actually have a proper 85032 kit, and then I have with that, and then with the VNA that I have, or with the directional couplers and a power meter and my 8400 sensors. I would actually be able to set that up to get the exact reading and that. Anyway, so if we take a look at the little math for it, basically, the reflection coefficient value is going to be the load minus the system impedance with the load plus. Now, the system impedance 50 ohms, and because these are going to be in parallel, that'll give us 25 ohms. So if we do that math, we get a resultant coefficient of 0.3 repeater.
Sure.
Now, the formula for the VSWR is basically 1 plus the absolute coefficient 1 minus. And that results in a VSWR of 2. And if we look at what our return loss should be based off that coefficient, we should get around minus 9.5 dBm on the return loss.
Okay.
So knowing those figures, we now have some idea what we'll see coming out of this. So the first thing I want to do just to show this is just going to turn on the output of my the output of my 8340B. And what you can see here is we're reading. What
are your settings on the 80B?
This is it's continuous wave, 0 dBm, 100 megahertz. So we're right at the bottom of the thing, but it is what it is. And my 8340B hasn't been leveled properly. I have to get in, and I fixed it up so that it basically works across the frequency range.
I love this right here because it has the log part.
Yeah, well, now you're reading it in dB microvolts, right?
Well, I'm saying like it's easy for me to think because I know everything is microvolts and
Right.
millivolts, and most of the things I deal with are dB, but it makes me mad because I always get dB, dBc, dBms like in my head confused. So I'm just thinking it's all millivolts though,
Right?
Microvolts and millivolts.
Well, it's that system impedance. You got to know that to be able to convert back and forwards between them and so
gotcha.
on. But anyway, if I go over here and I press the power measurement, you'll see that we're reading 6.4 microwatts, and if I tell it to display that in dBm, I'm now getting minus 21.9 dBm. Now, the reason I'm getting minus 21, even though it's set for 0, is because of on this directional coupler, basically on each coupler you'll get a 20 dB loss.
Gotcha.
Now, if you want to actually just pass me that clipboard over there.
Yeah. I don't want to drop my fingers.
Yeah. So what you can see here is this is actually a test of the directional coupler. And if you were using this in a real test environment, you'd know exactly what the
frequency and
how much am I losing on the transmission line, on the strip line through it. What is the incident at that frequency? Really, it's going to be minus 21 instead, or minus 20.4 or something. Right. You'd be able to take that and then add that to your specs or to your measurements, if you wanted to do it that way. So what we're showing here is that we're at minus 21. Now, I can actually also turn on B, and what we're now seeing is that I'm getting minus 22.1, and what that's showing me is that that signal has come down here, hit this endpoint, bounced back, and I'm reading the reflected information back off there. There's a similar connection to this at the other end of this directional coupler. If I pull that across a little bit, that you can see that will show that's the incident. That's where I'm reading that 21.9 from. So that's the showing what I'm getting there. Now, I want to measure that SWR. So that's a reflection measurement.
So in this scenario, this would be a good, if you had your UT at the end of that, get all your references, and then you put your UT at the very end of that.
Right, and that's exactly what we're going to go do here. So what I'm going to go do is come over here into my reflection measurement, and I'm going to start with SWR, and so I want a short. I'm going to put my short on, and then I'm going to save my reference. Okay, so now that I've done that,
and the 3 slashes were the indication that it took its reference, right?
Yeah, because we're measuring SWR, it's saying like it's 150.
Yeah.
So on, if we were to go back and measure absolutes, you would see the millivolt and so on. So now I can take this guy and I can drop this guy on.
Tell my wife, we're going to hang out, Tony. We're going to talk geek and drink.
All right, and so there you go. You're seeing that we're getting 1.96 ish
with the split.
With that, and the theoretical was 2.
Oh.
Right, so we're pretty damn close. Now I can do I can go back and say I'm going to look at my phase, and what I'm seeing is minus 9.74. This is minus 9.5.
Now you did that measurement with a short. Now, if you were to take just the one of those loads, do the load measurement, and then redo it with those both, would you have a more accurate measurement?
No, because the load measurement is really designed just for. It's my doggy. Sarah's taking him. My wife's taking him out for a walk.
Oh.
That load, that's designed for that open reflector, the T measurement, when you do the load there.
Oh.
Right? It's not like a VNA where you're taking, say, a 909F, which is a very highly accurate 50 ohm load.
Okay.
And what you want is basically everything to be absorbed, the entire signal to be absorbed, so that you know that you've got your matched
short first.
your matched load.
Took everything away.
The short is just what this system uses. In a proper VNA, you're going to use a short, an open, and a load to do your 2-port cal, right? So here we've got this phase and a magnitude that we're showing. Now, if we go back here, you can see the standard units. What I can also do is go down here to impedance, and now what we've got is we've got the impedance telling me that it's reading 25.5 ohms, and
is that deflection, the 2.8?
Yeah.
Okay.
And so now I forget how I should be able to do this. And now what we've got is we've got our complex impedance here.
Oh, shit.
Right, so here's our real part, 25.4, and our imaginary part, which is what the little j is 1.23 ohms.
Okay.
So you know how we talked about that Smith chart where it goes around, right? What you would take, this is the actual complex impedance measurement.
Okay.
You would be able to take this and normalize it. Because remember, the Smith chart is basically 0 to 1. And
is that just reactance? Is that reactance or is that something else?
Yeah, no, that's the reactance. You have impedance, reactance, reluctance.
Okay.
Which are the AC versions of resistance, capacitance, and
because AC is definitely different. I think,
because the AC you'll get these complex values, right, based on stuff. So. The
complex.
You would then take this and you would normalize the real and the things to get the position on the Smith chart, right? Okay. And that would tell you, and then you would move, but you would change the frequency and you'd move around and you would create your Smith chart.
Yeah.
This thing has a cool capability. I can go over to system load and I can hit normalize.
Oh my God.
And now it has actually normalized that Smith chart value. So if we look at this, if you remember how the Smith chart's working, 50 is going to be in the middle. Half is basically that middle point.
Okay.
And 2 is going to be 0.02 is right. So we're reading almost a perfect sort of. No, sorry, the 50 is not going to be the middle point. 50 is going to be the 25 point. It's going to be halfway to the 1, which is the normalized, right?
Bar, but still pretty damn small.
So and it's going to be it's very close to a pure 25 ohm load.
Everything out, everything back in.
Yeah,
essentially. Yeah.
And so now we've done the measurement here, and I can go measure different things, and I can look at.
Do you have a UT you can at the end of that? Like
what's
a cap or something?
No, I actually don't have a device that I can test at the moment. So
what?
I wanted to get. I need to get a little amplifier that I could just.
Theoretically, you better just take that off. It'd be an open, right?
Yeah. But you're going to see. Let me pull that up. Come on.
Because right now the number is the perfect reference, and then when you see an open, that's the measurement technically ish.
Yeah. See, so now you're not getting 25. Now you're getting 70.
Which always vary because your RF's just coming out there like a spout of water, and
right.
This is the hardest part of RF is stabilization. For me, it's like, there we go. Nice.
So we can do that power.
It's so sensitive, though.
Yeah.
I used to have a unit at Raytheon because that's part of my experience that I'm willing to talk about because it's done. But we had this a Maury microwave, and Maury's not around no more. Or they're not.
No, Maury microwave is,
or this.
Probably not the device.
Yeah, whatever this device was, it was something that we had to plug in for days. And when I got it calibrated, it was, okay, everybody synchronize because I'm going to unplug it and I'm coming across the street to bring it to you to plug it back in the same day.
Right.
But that was a stabilization issue.
Yeah.
That's the biggest thing about RFIC, and this is great.
Well, so a lot of these units, they'll tell you in the service manual, like or they'll tell you in the manual how long before you can read that you can trust the values that are going to come out because the components heat up and they reach steady state and all that sort of stuff. This particular unit's about half an hour.
Okay.
Which I think is probably pretty typical for most of the gear of this era. Some of the more sensitive gear, like they'll tell you that, like my 89, I think my 8092A is 30 minutes for one set of specifications and then 24 hours for another set.
Sure.
And stuff like that. So
yeah.
It's all in the manuals, but I usually just go for about half an hour prior to taking a measurement.
Well, in the military, we used to, 45 minutes was the recommended time for warm-up for everything. But we do all the testing within 20 minutes. And if it fails, you let it warm up then. If it doesn't fail, it's okay by that point. Because the oscillators, within minutes if it's aged or not, a unit. But they're all bound to degrade.
I'd like to take the opportunity to say that's why I was in the Army and not the Navy. So yes, you can definitely do that. There's a little risk though, because the unit, you might get some false passes where a device is actually just outside of a spec.
Yeah.
And as you warm up, your actual measurement window moves past where the device is. But typically these things, I think where you're going is typically a lot of this stuff is either in spec or it is way the hell out.
Yeah.
Right? I have not seen anything that I've bought on eBay or from auctions or from pulled from working environments that has come in where it's been just sitting outside of the spec.
Yeah. It's just like a couple times I've dealt with in my test and measure experience has been, I fail a unit, and then and again I'm using OEM procedures and OEM process, which is 100% just legit, and I'm like, all right, it failed, but because the customer, I really want to try my best, and I doubt myself. I leave a unit plugged in. Even after I pass the 24-hour warranty period, if it's a, say, 20-year-old piece of equipment or 15-year-old,
right.
If it's older equipment, you got to give it time. And that's what I do. So I failed a unit, and then say the next day I come back and be like, okay, you know what, one more time. And then everything passes repeatedly.
Right.
It tells me it's the oscillator.
Yeah, you've got to go have a look and see if it will pass. So I have a problem with one of my favorite signal generators is this 8657B that I have over here. Excuse the camera wander, but this is the device here. This is a fantastic little signal generator, and when you first turn it on, it generates. It has quite a significant amount of frequency modulation on the output signal, which it's not supposed to have.
Yes.
So it fails to generate a clean signal. And in fact, it has enough frequency modulation that the 8508A can't lock to it. That's how I found it. I was originally going to use that as my input.
Oh, shit.
And I found that it wouldn't lock. And so I was wondering, is the problem in the Vector Voltmeter or the problem with the SIGGEN? And so eventually I did put the SIGGEN on the spectrum analyzer and looked at it. You could see the classic FM sort of modulated output instead of a single nice spike on it. But if you leave it running for enough time, that goes away.
Yeah.
And so there is a problem, right? So that it is not working to spec, it's not working properly.
Clearly.
But I have to take it out of the rack and then go through. It's on my list of projects to do. Anyway, that gave you a quick look at what an 8508A is, a vector voltmeter, and how to do a simple measurement with SWR, and some extended commentary as it went on there. So I hope you guys found that interesting. Please subscribe to the channel. If you have any comments, especially if you have some insight in the antenna exciter question.
That'd be interesting.
Yeah, drop it in the comments below. I'd love to see it. Also, hang around. We're going to have a little more of a chat to Miguel with a couple of photos of the racks that he has at his little test facility. Anyway, thanks for watching. Catch you later. Bye.